Assalamu alaikum warahmatullahi wabarakatuh.
Welcome to the deep dive. Today, we're tackling something pretty intense, building a Formula Student race car. But get this, doing it completely solo.
Yeah, it sounds almost impossible, doesn't it?
Ah,
You, our listener, are probably thinking, how on earth does one person even start that? And what do they learn?
exactly. So our mission here is to really dig into that. We want to pull out the key strategies, the big insights for anyone attempting a solo Formula Student build.
Right. We've gone through a ton of material advice from competition vets, serious engineering papers, practical guides, you name it. We're aiming to give you the shortcut, basically.
Understand the hurdles, the solutions.
Yeah, the technical stuff, the resource limits, even how you might, gamify it to stay motivated.
Gamify building a race car.
Okay.
Interesting. And we've looked at drivetrain choices, electric versus ICE.
Project management for one person's car setup, self-assessment, how to learn from cars that already exist.
Specific solo guides, research reviews, active aero, tire pressures.
How to handle roadblocks, because there will be roadblocks.
Oh, definitely. Budget building, electric design. It's a lot.
It is. So let's dive in. Let's unpack this massive challenge of going it alone.
Okay, so first off, just how hard is it? The sources really paint a picture, don't they?
They absolutely do. It's not just one thing. It's
Mhm.
technical hurdles, logistical nightmares, and just, well, not having enough stuff resources, all hitting one person.
Let's start with resources then. Money, obviously. Big
Yeah.
one.
Huge. Forget team sponsors knocking on your door. You're looking at crowdfunding, maybe, or seriously scrounging.
Like literally junkyard parts.
Yeah, the sources mention finding motorcycle engines in junkyards. It forces incredible resourcefulness, turning nothing into something.
Okay, so resourcefulness is key. What about tools? You can't just pop down to the university workshop.
Exactly. Access to the big stuff. CNC mills, TIG welders.
Yeah.
That's a major problem. Often means outsourcing.
Which costs money you probably don't have.
Right. It spirals, adds cost, adds complexity.
And time. The sheer amount of time needed.
Oh, it's staggering. Consistently, the sources point to over 1,000 hours, minimum.
1,000 hours, that's like a full-time job on top of whatever else you're doing. Studies, work.
It's a massive commitment. Shows incredible passion, really.
Okay, so resources are tight. What about the technical side? It's not just bolting bits together, is it?
Not even close.
Yeah.
You need expertise across so many different fields. It's seriously multidisciplinary.
Like what specifically?
Well, chassis design, for starters. That means finite element analysis, FEA,
Which is like virtual stress testing.
pretty much.
Yeah.
Seeing how the frame holds up under load digitally. You're aiming for serious stiffness over 2,000 Newton meters per degree is a common target.
Okay, so structural engineering. What else?
Electronics, all the wiring, sensors, data logging systems, that's a whole field in itself.
And aero. Gotta make it stick to the track.
Right. Aerodynamics, computational fluid dynamics, CFD simulating airflow, trying to get a good lift-to-drag ratio, maybe 1.5 or more.
Downforce versus drag. Critical balance.
It's a lot of specialized knowledge for one brain to handle.
Which raises the question, how do you learn and apply all that? And the rules.
Oh, the rule book,
Yeah.
often over 300 pages long. And you, the solo builder, are responsible for all the documentation.
Like weld logs, cost reports.
Every single weld, every single part costed out, meticulously. It's a huge administrative burden on top of the engineering.
Okay, let's talk making stuff. Manufacturing, that's gotta be tough alone.
Very. Precision is key.
Yeah.
Think about TIG welding the chrome lead tubing 4130 steel.
Right, keeping it from warping under the heat.
Exactly. You need proper jigs, really careful heat control. Not easy without experience and the right setup.
And if you're ambitious, maybe a carbon fiber monocoque?
Even harder. Needs controlled environments, vacuum bagging. Serious stuff. Not your typical garage setup.
And quality control. How do you even check your work properly?
That's a big limitation. Teams have access to non-destructive testing, NDT, like die checks for cracks or ultrasonic testing.
Stuff you can't really do on your own.
Not easily, no. So there's an element of just hoping it's right.
And when it comes to testing the finished car, validation.
Also hampered, you don't have a team of experienced drivers giving feedback to tune the suspension.
Right, you're probably the only driver.
And telemetry might be basic. You're trying to optimize cornering Gs, stuff like that, but maybe without much real-time data.
Makes iterative improvement really hard, doesn't it? Less data, slower progress.
Exactly. And safety risks are very real. Testing a roll cage properly, that needs specialized rigs to apply the required force.
Something a solo builder just won't have.
Nope. So logistics and just competing, More hurdles.
Definitely. The sheer volume of paperwork for design reports, cost submissions, it's immense for one person.
And the actual dynamic events, autocross, endurance.
You're out there alone. No pit crew for repairs or driver changes. A huge disadvantage.
It really highlights the team aspect of Formula Student. Even the quizzes on rules like the brake system plausibility device, the BSPD.
The EV safety thing?
Right. Teams have specialists who know that stuff inside out. Solo, you need to know everything.
And psychologically, the mental toll.
Burnout is a massive risk.
Yeah.
No team support, nobody to share the load or the stress with.
Plus, mastering CAD like SolidWorks and FEA like ANSYS and actually being good at machining.
It's incredibly rare for one person to have all those skills at a high level. It's just a lot.
Okay. Point taken. It's monumentally difficult.
Yeah.
But people try. So what smart strategies can they use? How do you mitigate some of this?
Right. The sources offered some clever tactics. A big one is modular design,
Meaning?
using off-the-shelf parts as much as possible. Think Willwood pedal boxes, things like that. Components that are already engineered and proven.
So you focus on integration, not reinventing every single part.
Exactly. Leverage existing expertise. Saves a ton of design and manufacturing time.
Makes sense. And virtual tools, they must be crucial.
Absolutely essential.
Yep.
Free or low-cost software like SimScale for CFD, FreeCAD for design. They let you do a lot of validation virtually.
Test designs on the computer before making anything physical.
Yeah. Less trial and error, less wasted material, less cost. Critical for a solo budget.
And partnerships. Can you team up in other ways?
That's another smart move. Maybe collaborating with a local workshop.
Like trade design work for access to their CNC machine?
Potentially, yeah. Or welding help. It addresses that tool access problem. A win-win if you can swing it.
Okay, those are practical. Now, you mentioned gamification. How does that work?
This was a really interesting concept we found. Basically, turning the whole massive project into, well, a game.
Like levels and points for building a race car.
Sort of. Imagine hitting a big milestone, like finishing the chassis CAD model. That's level 1 complete. You get XP.
Okay. Keeps you motivated.
That's the idea. It taps into that sense of accomplishment. Maybe tiered rewards, digital badges.
Like FEA Master or Welding Wizard.
Exactly. Using systems like you see in online learning makes progress feel tangible. Less like an endless slog.
You could track progress visually too, right? Like a personal leaderboard.
Yeah, track your weekly progress against your own past performance. Use a project tool like ClickUp or Trello, or even habit trackers for consistency.
Like keeping a streak going for hours worked.
Right. It breaks down this overwhelming thing into smaller, achievable, rewarding steps, which is key for any huge project, really, not just this.
It adds elements of fun, self-competition, clear progress.
Exactly. Micro rewards, too. Finish a small task, like analyzing one bracket, take a 5-minute break, positive feedback loops.
What about unlocking things, like in a game?
That's a clever one, too.
Okay.
Maybe you only unlock the CFD software once you've demonstrated you understand the basics of fluid dynamics.
Course structured learning builds a solid foundation.
Yep. And social accountability, even solo.
How? Post your progress online.
Yeah. Commit to milestones publicly. LinkedIn, Reddit forums, use a hashtag #FSProgress. Creates a bit of pressure, gets you encouragement.
We're virtual pit crew.
Kinda. And tools can help virtual trophies in Notion, XP calculators, and spreadsheets.
You could frame the whole thing in levels. Rookie, veteran, elite.
With badges. CAD Ninja, Master Welder, Data Guru.
And track key metrics. Time efficiency. Cost savings.
Gamify it all. Gold Saver for budget wins, Precision Pro for quality work. It's about staying motivated, tracking progress, celebrating the small wins.
Okay, gamification. A surprisingly powerful tool, potentially. Let's switch to the heart of the machine, the drivetrain. Electric or internal combustion. Big choice.
Massive decision for a solo builder. Huge implications for complexity, cost, skills, everything. And the sources really dug into the electric option, especially salvaging parts.
Salvaging from what?
E-bikes, mostly. Surprisingly powerful components available. Mid-drive motors like Bafang or Bosch units can have serious torque, over 120 Nm.
Enough for a lightweight race car.
Potentially, yeah.
Yeah.
Or hub motors, simpler mechanically, maybe trickier to adapt.
And batteries. Can't salvage those, surely.
You can, actually. Standard cells like 18650s or 21700s from used e-bike packs, even laptop batteries sometimes. Build your own pack. Cost-effective, but needs care.
And the controllers. The BMS.
Sometimes those can be repurposed, too. The battery management system is vital for safety and managing the cells.
Okay, so you've got salvaged bits. How do you put it together? Architectures.
A common route is single motor, chain drive to the rear axle. Simple, relatively budget-friendly. Choose your sprockets for the right gear ratio. Add a mechanical spool diff.
Cool diff. Both wheels lock together.
Yep. Simple, effective for traction. Or, more ambitiously, dual motors. Maybe hub motors.
For more power. Or control.
Both. You could even attempt basic torque vectoring, controlling each motor's speed independently with an Arduino, maybe PWM signals. Enhances handling.
Wow, that's pretty advanced for DIY. What about fabrication? Mounting motors, etc.?
Custom motor mounts are usually needed. Laser-cut aluminum is common. Vibration damping is important too.
And aligning the chain drive.
Critical. Needs precision. Custom tools, careful measurement, 3D printed chain guides can help too.
Building the battery pack sounds delicate and dangerous.
Needs extreme care. Modular design helps build smaller packs, connect them. Nickel strips usually spot welded. Thermal management is key. Fans, thermal pads. Gotta keep it cool.
And controlling the power, getting it from the battery to the motor.
Often involves modifying an off-the-shelf motor controller. You need a throttle system, usually potentiometer-based. Plus, safety circuits, pre-charge circuit, low-voltage monitoring.
How do you optimize performance with salvaged stuff?
Weight distribution's huge. Battery pack, low and central. Maybe counterweights needed. Regenerative braking is a big plus. If you can implement it, recovers energy. Good bus bars minimize electrical losses.
Sounds like lots of potential for cost saving here.
Definitely. Salvaging sensors, throttle grips, building your own spot welder for microwave parts, using plywood for jigs. Very resourceful.
But safety rules still apply, right? Even with salvaged parts.
Absolutely non-negotiable. Proper high-voltage cabling, compliant shutdown circuits, mechanical guards for chains, polycarbonate shields.
Well,
all mandatory.
And teams have done this successfully. Budget EVs.
Yeah, we saw examples. Kayet Hermes got decent power from repurposed motors. Team Tachyon used hoverboard motors for torque vectoring. Shows what's possible.
Incredible ingenuity. Okay, so how does this salvaged EV approach stack up against a traditional ICE build for a soloist?
Key differences. Electric, often quicker acceleration in FS context. Torque control is more precise, electronically torque vectoring versus mechanical LSDs in IC cars.
Efficiency.
Much higher for electric, 85–90% versus maybe 15–25% for IC. But energy storage is different heavy batteries versus lighter gasoline.
Electric gets regen braking too.
Right, recovers energy, IC gets none. But EVs have challenges. Electromagnetic compatibility, high voltage safety. IC has fuel rules, emissions.
And cost upfront.
Electric powertrain often costs more initially, maybe $15K, $25K, versus $5K, $10K for a basic IC setup, though running costs might differ.
So it's a strategic choice. Innovation and dynamics with EV, maybe cost and familiarity with ICE.
That sums it up pretty well for a solo builder. Big decisions either way.
Okay, regardless of powertrain, it's complex. How can a solo builder avoid reinventing the wheel? Leverage existing knowledge.
Absolutely critical strategy. Stand on the shoulders of giants, basically. Don't start from absolute zero.
Like using existing chassis designs.
Exactly. You can often find public space frame designs from past teams. Designs that are already proven, already hit that stiffness target we talked about, saves huge amounts of time. Or get inspiration from successful monocoque structures.
What about suspension? That's complex geometry.
Yep. Use existing blueprints. Well-engineered double wishbone kinematics are out there. You can even find CAD files for uprights on places like GrabCAD and modify them to fit your car. Good starting point.
Aerodynamics, can you borrow ideas there too? Seems very specialized.
You can. Use proven high-lift airfoil profiles like the Selig S2223 was mentioned. Adapt wing package designs that other teams have shared. Designs already validated with CFD. Gets you in the ballpark without being a CFD guru yourself.
Electrical systems, wiring, battery layout.
Less common, but yes. Example wiring diagrams from open source projects, basic battery layouts from EV teams, they can be a starting point.
Safety components, impact attenuators, roll page padding.
Definitely. Find validated impact attenuator designs that meet the energy absorption rules. You can buy pre-cut, certified roll cage padding templates, streamlines safety compliance.
So the community is a massive resource. Open source designs, forums.
Hugely valuable. Public CAD documents, simulation templates, great for someone without expensive commercial software.
Even documentation. Can you use templates for cost reports and stuff?
Yes. Example bills of materials, even FEA validation files. Gives you a structure, shows the level of detail needed, saves time figuring it all out from scratch.
So it's smart adaptation, not just blind copying.
Precise. Modular updates are key. Keep maybe 70–80% of a proven design. Focus your effort on upgrading one key system, but always double-check everything against the current rulebook. That's vital.
And the time saving could be huge.
Potentially 30–50% reduction in development time, the sources suggested. That could be the difference between finishing and not finishing. Solo.
Game changer. Okay, let's talk project management. The solo builder is the engineer, mechanic, and the manager. How do they succeed?
It's absolutely fundamental. Good management is non-negotiable. A key strategy. Reverse engineer the deadlines.
Work backwards from the competition date.
Exactly. Set clear milestones for each phase. And be realistic. Probably double your initial time estimates for everything. You're doing it all alone.
Good advice. Break it down into chunks.
Modularize the build. Component phases. Suspension steering first, then chassis, powertrain, electronics, bodywork. Validate each stage. And make smart buy versus build decisions. Buy complex stuff if you can.
Documentation must be a beast solo.
Brutal but essential. Daily logs, decisions, problems, solutions. Vital for troubleshooting and the final tech inspection reports. Set firm design freeze dates too. Stop scope creep.
Can you still collaborate virtually? Get feedback.
Gotta leverage that. Use the forums, RFSAE on Reddit, Discord channels. Share designs, ask questions, maybe even do virtual design reviews with alumni or mentors.
Risk management. How do you anticipate problems alone?
Need a system. FMEA failure mode and effects analysis for critical stuff like brakes. What could fail? What's the impact? How do we prevent it? Dual circuits, pressure sensors.
And budget for things going wrong.
Absolutely. Build in a contingency, at least 20% of your budget for unexpected costs, rework, outsourcing emergencies.
Testing solo. No team of drivers or data gurus.
Phased approach. Static tests first, then low-speed shakedowns, then performance testing. Use affordable data loggers, aim solo, things like that. And practice the static events too, design judging, business presentation.
Optimizing resources must be constant.
Always. Look for tool-sharing opportunities, makerspaces. Sponsor pitches, even small logo placements might get you materials.
It requires serious self-discipline.
Totally. Time blocking helps. Kanban boards in Trello or Notion for visual tracking. Stay organized, stay focused.
And know the rules inside out.
Meticulous rule checks. Create inspection checklist referencing specific rules, firewall thickness, BSPD function. Prepare a spares kit for competition. Don't get caught out.
Finally, staying sane. Mental resilience.
Crucial. Pomodoro technique for focus. Peer support networks connect with other solo builders, alumni. Share the struggle.
So it's planning, virtual teamwork, documentation, risk management, self-discipline, resilience. A massive management task on top of the engineering.
It really is. Now, assuming the car gets built, setup, fine-tuning performance, how does a soloist tackle that complex process?
Yeah, without a data team, it seems tough, but possible.
Possible but different. You adapt the professional data-driven approach. Focus shifts to rule compliance, lots of virtual validation, and carefully interpreting limited real-world feedback.
Simulation becomes even more critical then.
Hugely. Suspension kinematics software, Optimum K, AtomScar lets you analyze camber change, toe variation, anti-dive squat virtually. Aim for targets, like minimal toe change.
Can you use AI or machine learning? That sounds advanced.
There's research on using ML to predict optimal setups from simulation data. Probably beyond a first solo build, but the idea of using data smartly is key.
What about cheaper real-world testing?
Skid pad testing is valuable. Measure max lateral Gs. Use affordable IMUs to log data. Correlate it back to your simulations. Even basic driver feedback your own is useful if structured.
Driver in the loop sims, like Assetto Corsa.
Yeah, with custom car models. Can give you a feel for setup changes before hitting the track. Cost-effective way to experiment.
How do you innovate on setup solo within the rules?
Focus on modularity. Quick release aero packages for easy adjustment. 3D printed parts for rapid prototyping of non-structural bits. And document everything. Link your simulations to your design and report justifications.
Teams have shown big gains from setup optimization, right?
Definitely. ETH Zurich got lap time improvements optimizing suspension. Oxford Brooks used deep learning for setup games. A solo builder won't have those resources, but the principle applies. Systematic testing, careful analysis of whatever data you can get.
So combine virtual tools, focus testing, basic data, and solid engineering understanding. That's the solo setup path.
Pretty much. Informed decisions based on the available tools and data.
Yeah.
Okay, so planning, building, testing, setting up. How do you know if you're actually on the right track? Self-assessment seems vital solo.
Absolutely vital. Without team feedback, you need structured ways to gauge your own progress and find weaknesses.
What kind of frameworks help?
The solo taxonomy was mentioned. It helps assess your level of understanding from basic to deep. Custom rubrics are good too. Define criteria for weld quality, CAD accuracy, rate yourself, And SMART goals, of course.
Specific, measurable, achievable.
Relevant, time-bound, keeps you focused, tracks progress.
Still need external feedback though, right? Even solo.
Definitely. Iterative feedback loops. Share stuff on forums, get critique. Find virtual mentors if possible, alumni, industry folks. Even AI tools for checking documentation, grammar, and clarity. How do you track progress quantitatively? Make it less subjective.
Time logs are good. Toggle, spreadsheets. See where your time actually goes. Milestone tracking with percentages complete. Maybe a personal skill matrix, rate your CAD, welding, electronic skills periodically, see improvement.
And reflection. Stepping back and thinking about it.
Crucial. Keep it journal challenges, insights, lessons learned, video diaries maybe.
Yeah.
Quarterly SWOT analysis, strengths, weaknesses, opportunity, threats for the project. Gives perspective.
How do you benchmark your skills or the car's performance against standards?
Compare your simulation results, FEACFT,
Yeah.
to published papers or known team results. Do physical tests if possible, load cells on suspension parts, and constantly audit against the rulebook. That's a key benchmark.
Any digital tools that really help with self-assessment?
Project boards like Notion or Trello for visual progress. Version control like GitHub for tracking design changes. Even Excel macros for automating checks, like against cost report rules.
And this structured self-assessment actually works, improves things.
Research suggests yes. Solo taxonomy improves self-evaluation accuracy. Peer assessment, even online, reduces errors. It helps you see your blind spots.
So a mix of frameworks, feedback, tracking, reflection, benchmarking, and tools. That's the solo self-assessment toolkit.
Sounds about right. Needs consistency weekly, monthly, quarterly checks. Essential to stay on course and keep improving alone.
Okay, let's pull back again, the big picture. Someone is seriously thinking, maybe I could do this solo. What's the comprehensive view?
Comprehensively, it's an extraordinary challenge. Requires deep knowledge across a huge range of engineering materials, aero, suspension, engines or batteries,
Yeah.
manufacturing. It's immense.
Far beyond a typical student project.
Way beyond. Realistically, a solo Class 1 build is a 2-3 year commitment, minimum. Starting with Class 2, the design-only competition is a much more achievable first step for an individual.
And the money, still significant.
Oh yeah, $15,000 to $20,000 is probably the absolute minimum for a basic but functional car. Easily more. It's a serious financial undertaking.
You need a proper workspace,
Yeah.
right? Tools.
Critical. Dedicated space. TIG welder, mill, lathe, tube bender. Specialized tools. Might need to partner with machine shops or trade schools for access.
Constant learning is a given.
Absolutely. Reading the key texts, Carol Smith, Millikan plus software tutorials, FSAE resources. It's continuous self-education. And the philosophy should probably be, buy what you can, focus on integration.
Keep it simple, especially first time.
Definitely. Stick to a logical design sequence. Maybe avoid composites, complex aero, or EVs for the very first attempt unless you have specific prior experience. Focus on fundamentals.
So planning, budget, workspace, tools, knowledge, all need to be solid.
Foundational. And you have to be honest about the downsides. The massive time sink, the breadth of knowledge needed, the financial strain, the lack of built-in support you get in a team.
Are there alternatives people should consider first?
Yeah, the sources suggest evaluating options. Simpler projects. Joining an existing team to learn the ropes. Forming a small team instead of going truly solo. Starting with Class 2, these might be more practical paths.
But if you do go solo and succeed, the learning must be incredible.
Unparalleled. The depth and breadth of practical skills, design, build, test, manage. It's an education you can't get any other way. Hugely valuable, despite the immense difficulty.
Okay, given that difficulty, what are the absolute killer pitfalls, the common mistakes that sink a solo project?
Time underestimation is probably number one. Thinking you can do it in a year. Realistically, budget 2-3 years, break it down into tiny steps. Remember, teams put in thousands and thousands of hours.
Right. What else?
Rulebook neglect. You have to know it intimately. Technical rules, safety rules, student participation rules. Miss something critical and you fail inspection or worse.
Poor planning. Starting to build too soon.
Big mistake. Finalize designs in CAD. Validate key systems with simulation first. Stick to a strict design sequence. Rushing into fabrication leads to rework and despair.
Making it too complicated. Feature creep.
Very common. Keep it simple, especially the first time. Steel tube frame, reliable motorcycle engine, off-the-shelf brakes, and steering. Focus on making that work well. Avoid exotic materials or overly complex systems initially.
Skimping on testing.
Fatal. You need static tests, low-speed shakedowns, then performance tests. Document everything. Find the flaws before competition or before something breaks badly.
Financial mismanagement, running out of cash.
Easy to do. Need a realistic budget with contingency. Source used parts smartly. Get sponsorships for materials if you can. Avoid costly custom parts unless absolutely necessary.
And working in a vacuum, ignoring feedback.
Even solo, you need external input. Share designs on forums. Get critique from mentors. Don't assume you know everything or haven't missed something obvious. That isolation can be dangerous.
So, realism about time, rule mastery, solid planning, simplicity, rigorous testing, budget control, and seeking feedback. Avoid those pitfalls.
That's the essence of it. Okay, let's pivot slightly. For the really ambitious solo builder, maybe thinking beyond the basics. Any advanced concepts or overlooked areas from the sources? Food for thought.
Yeah, what's often missed or underexplored?
Well, things like integrating a steering wheel display for critical data, tire pressures, temps, or a properly adjustable pedal box that's even in the rules sometimes. Maybe flexible aero end plates, or experimenting with ground effect tunnels and adjustable ride height advanced aero stuff.
What about systems? Stuff beyond the obvious.
Deeper dives into thermal management, phase change cooling for batteries, exhaust gas recirculation for ICE efficiency, optimizing the CAN bus network, really nailing the HVIL circuit design in EVs,
Yeah.
verifying welds beyond just visual checks, ensuring cockpit templates are met precisely.
Operational stuff, too. Things beyond the car itself.
Quick change battery modules for EVs sub 60 seconds. Modular suspension for fast setup changes. Really detailed documentation for salvaged parts for the cost report. Life cycle analysis for tires, brake pads.
And the human element. The driver.
Using simulators to validate controls. Neck conditioning. Vibration damping on controls. Optimizing emergency egress time sub 5 seconds. All important details.
Any really cutting-edge ideas mentioned?
Brief mentions of things like magnetorheological dampers, dynamic aero beyond, basic DRS, graphene composites, self-healing polymers. Probably future tech, but interesting.
Competition strategy beyond speed.
Detailed failure analysis for the judges. Cross-referencing cost reports meticulously with CAD. Data-driven tire temp management. Endurance pacing algorithms. Thinking strategically about the static events.
Gaps in knowledge or validation. Things we still don't fully understand.
Simulating cold weather EV starts. Testing partial failure modes. Mitigating gear whine or panel resonance. Documentation traceability like lot numbers for fasteners, composite cure reports, correlating FEA perfectly without a rig.
Key unanswered questions.
Things like fail-safe throttle-by-wire design, best CFD turbulence models for this scale, validating stiffness without a dedicated rig. Still areas of active research and debate.
Sounds like digging into the EV rules, T12 structural rules out in T3, and the design event score sheets is key for anyone wanting to innovate strategically.
Absolutely. Understand the constraints and judging criteria deeply. Okay, let's talk about making it stick. Aerodynamics, sleek and fast. What's happening there? Active aero.
Yeah, active aero is getting big in FS, trying to get the best of both worlds, low drag on straights, high downforce in corners.
Like DRS and F1.
Exactly. Drag reduction systems, manually activated flaps, usually on the rear wing, reduced drag by maybe 35% on straights, helped acceleration, top speed.
Significant gain. What else is active?
Fluidic actuators are interesting. Tiny air jets on wing surfaces, blowing air. To do what?
To keep the airflow attached at higher angles of attack. Delays flow separation. Can boost downforce significantly over 20% in some tests. Needs careful control of the airflow, though.
So more downforce without just adding massive wings.
Potentially.
Yeah.
And optimizing multi-element wings is ongoing. Adjustable flap angles, removable elements,
Right.
all driven by CFD analysis using tools like NSYS, Fluent, or SimScale.
Any weird surface stuff? Textures.
Research into surface texturing dimples, ridges to manipulate the boundary layer, reduce drag. 3D printing makes complex textures feasible now.
Can you combine these active systems?
That's the next step. Integrating DRS with fluidic actuators, maybe active flow control. But keeping the actuation systems lightweight and energy efficient is key. Pneumatics, low-power electrics.
How do you know when to activate this stuff?
Predictive strategies. Lap simulations to find the best spots on track. Maybe driver assist algorithms using GPS, speed, throttle data. Getting quite sophisticated.
Gotta keep the weight down, though, right?
Yeah.
All these mechanisms.
Crucial. Carbon fiber linkages, quick release systems for easy adjustment and maintenance. Minimize the weight penalty.
And how do you know if it actually works? Validation.
Wind tunnel testing is still important, often with scale models, and on-track telemetry strain gauges on wing mounts, IMUs, to measure the car's response.
But it all has to fit within the rules.
Always. Focus on mechanical simplicity, avoid overly complex electronics. Modular designs help adapt to rule changes or track needs. Keep it compliant.
So active aero is a big area of innovation, trying to find that grip-drag balance cleverly.
Huh?
Okay, sticking with grip tires, finding that optimal pressure. Seems like black magic sometimes.
You can feel like it. But it's really a methodical process. Blend manufacturer guidelines, physics, and testing. Find that sweet spot for grip, wear, handling.
Where do you start? Just pump them up.
No. Start with the tire manufacturer's baseline. Hoosier, Avon, Goodyear. They all give recommended hot pressure ranges, often linked to target tread temperatures. That's your goal.
Hot pressures. Okay, but you set them cold. How do you figure out the starting cold pressure?
Calculations help. You can use the ideal gas law estimate cold pressure based on target hot pressure and expected temperature rise. Needs ambient temp, estimated tread temp increase.
It involved any simpler way.
Rule of thumb is using a scaling factor. Divide your target hot pressure by maybe 1.2 to 1.5. Gives you a starting point for cold pressure.
Okay, so you calculate a starting cold pressure, then hit the track.
Yep, standard protocol. Set the cold pressures, do a short run, maybe 3-5 laps, get heat into them. Immediately measure the hot pressures.
And adjust.
Exactly, too high, bleed air, too low, add air, repeat. Small adjustments between runs until the hot pressures are stable and in the target range.
That gets you in the ballpark. How do you fine-tune for max performance? Go beyond the recommended range?
Maybe slightly, carefully. Advanced stuff involves traction circle analysis, maximizing combined braking cornering Gs. Sometimes peak grip is at slightly lower pressures within the safe window. Also consider vertical stiffness, how much the tire deflects. Pressure affects contact patch shape.
What are the mistakes? Pitfalls?
Overinflation is common. Reduces contact patch, less grip. Underinflation causes excessive wear. Heat buildup can damage the tire. And keep pressures balanced across axles, usually within 1 psi side to side.
Tools needed for this. Beyond a gauge.
An IR pyrometer is crucial, measures tread temps across the width, inner, middle, outer. Shows how the tire is working, contact patch, alignment issues. Real-time pressure sensors are great if you can afford them. Maybe CFD or tire modeling data for really deep analysis.
Small changes can make a difference.
Huge difference. Case studies show finding the right cold pressure, maybe dropping a few psi's from the initial guess, can gain seconds per lap. It's critical setup work.
Definitely not just setting and forgetting. Okay, inevitably, things will go wrong during a solo build. Roadblocks. How do you handle them without a team to help brainstorm?
Yeah, hitting a wall solo can feel disastrous. But having a structured approach and a resilient mindset is key.
First reaction when something breaks or doesn't work.
Don't panic. Analyze. Quick SWOT analysis. What strengths do I have? What weaknesses is this exposing? Any opportunities for a workaround? What's the threat to the project? Then, the 5 whys. Drill down to the real root cause, not just the symptom.
Get past the frustration, understand the why. Then what? Solutions.
Be adaptive. Break the problem down. Trial and error may be using those salvaged parts for experiments. Brainstorm, use online forums, bounce ideas off virtual mentors. Even AI tools can sometimes offer suggestions now.
What if the roadblock needs stuff you don't have? Tools, materials.
Resource management kicks in again. Go back to sponsors. Explain the specific need. Look for tool substitutions. Can a makerspace help? 3D printing service. Virtual validation can simulation test a fix before you spend money.
Mindset and workflow matter too, right? Staying positive.
Hugely. Pomodoro sprints can help break down the problem-solving work. Reframe, this isn't failure, it's learning. And document everything, the problem, the diagnosis, the solution. That's valuable knowledge for later.
Plan for problems from the start.
Contingency planning. Modular design helps isolate issues. Build in time and budget buffers for rework. Cultivate that network for advice when you get really stuck.
Good to know setbacks are normal and solvable.
Absolutely. We saw examples of teams and individuals overcoming huge hurdles. Systematic analysis plus resourceful flexibility. Roadblocks are part of the journey. Opportunities to learn.
Right, see them as challenges, not dead ends. Okay, back to resources, the budget. Always tight solo. Key strategies for building cost effectively.
It requires real strategic thinking. The main principle: prioritize rule compliance and core function over fancy stuff, especially early on.
Get the basics right, affordably. Specific areas for savings.
Simplify. Skip non-essential aero initially. Standardize fasteners. Use common sizes like M8 bolts everywhere possible. Buy off the shelf when it works. Avoid custom parts unless crucial.
Chassis and bodywork. Big ticket items.
Steel two-space frame is usually most cost-effective and strong enough. For monocoques, look at cheaper fiberglass aluminum honeycomb instead of pure carbon fiber. Impact attenuators, maybe aluminum honeycomb or clever 3D printed lattice structures instead of expensive pre-made ones.
Outsourcing, can that ever be cheap?
Sometimes. Laser cutting can be surprisingly affordable per part for complex brackets. 3D printing for prototypes or non-structural parts beats machining costs often, especially if you don't own a mill.
Powertrain and electronics, big costs there.
Salvage smartly. Used motorcycle engines, CBR 600R mentioned, are way cheaper than new. Affordable aftermarket ECUs like Speedwino and Chase sponsorships hard. Even small local businesses might donate materials for a logo.
Virtual tools help the budget too.
Definitely. Free FEACFG, SimScale, FreeCAD, free suspension kinematic software lets you optimize designs without costly physical prototypes.
What about brakes, steering, budget options?
Motorcycle master cylinders, GSXR 600. Affordable calipers like Willwood Dynapros, steering racks from common cars like MX-5 Miata or karting parts. Lots of ways to save compared to pure race spec stuff.
Documentation, can that save money?
Indirectly saves time. Reuse cost report templates. Accurately claim your student labor value as allowed. Use lean principles, minimize waste. Maybe use water jet cutting instead of slower CNC for some parts.
And teams have built cheap competitive cars.
Yes. Inspiring examples out there. University of Akron built one for around $12 in the 5Ks. Team Hermes cut chassis costs significantly using water jetting. Ingenuity and resourcefulness are key.
So careful planning, focus on essentials, resourcefulness. Budget building is possible. Okay, for the EV enthusiasts, let's dive deeper into electric drivetrain design, specifics.
Right. Designing an EV powertrain solo is a big step. Needs broad electrical and mechanical knowledge.
Architectures first. Single motor, multiple, AWD.
Single motor RWD is simplest, lightest. Dual motor RWD adds power, allows torque vectoring. Full 4WD with in-wheel motors offers ultimate control but much higher complexity. Choice depends on goals and skills.
Motor and inverter selection, what matters?
Power, torque, efficiency across the speed range. Weight. Brushless DC motors are common. Inverter needs to match motor specs, be efficient, have good control algorithms. SiC MOSFETs are becoming popular for efficiency.
Getting power to the wheels. Transmission.
Chain drive common for single motor. Hashtag 520 chain, maybe 4.1 reduction typical. Needs careful alignment. Planetary gearboxes for more power compactness. Direct drive is an option but has challenges.
Battery pack design. Cells, cooling, safety.
Cell choice is critical energy density like Samsung 50E, power, life. Pack voltage capacity based on targets. Often 7 to 8 kilowatts, 80 kilowatts limit. Thermal management is vital forced air, maybe liquid cooling, even phase change materials mentioned. Enclosure needs to be strong. Fireproof barriers. Robust BMS is non-negotiable.
Safety specifics for EVs. Rules are strict.
Very. Proper creepage distances, 2mm, FIA spec, TSAC, Tractive System Active Connector, strong battery box, 3mm aluminum, HVIL circuit, pre-charge resistors, lots of safety layers.
Control strategies. Traction control, torque vectoring.
Sophisticated motor control, field-oriented. Traction control is common. Torque vectoring essential for multi-motor setups to optimize handling. Isolated CAN bus for communication. Watchdog circuits for safety.
Simulation and testing for EVs. Even more critical.
Absolutely. Simulate endurance energy use. Optimum lap. Analyze motor thermal performance. ANSYS Maxwell. Dyno test the motor inverter. Rigorously test the battery pack. Vericki 5C discharge tests. Validate everything.
Fabrication challenges. Mounting, wiring, battery assembly.
Precision needed for motor mounts. 7075 T6 aluminum often used with damping. Careful high voltage wiring. Battery assembly needs care. Laser welded nickel strips common now. Modular segments help.
Cost management for EVs. Still possible to salvage.
Yes, salvaging e-bike motors batteries is viable. 3D printing for things like chain guides or composite shrouds saves costs. Smart component choices.
Case studies of successful FSEVs.
Metropolia Motorsport, known for 4WD torque vectoring. Technon Racing redesigned their DC bus for higher power. Lots of innovation happening. Key tools mentioned: SolidWorks, Altium for PCBs, Simulink for controls, FreeTOS for embedded systems.
Wow, deep dive indeed. Building an EV powertrain solo is ambitious.
Hugely ambitious, but possible with the right knowledge, planning, and execution.
Okay, let's try and wrap this up. This has been fascinating, looking at the sheer audacity of building a Formula Student car solo.
It really has, and the key takeaway is clear. It's a monumental undertaking. Needs incredible dedication, a massive range of skills, super meticulous planning, and serious problem-solving chops.
The challenges are huge, we've established that, but the learning potential.
Immense. Deep dives into design, fabrication, testing, management. It's an incredible educational crucible, leveraging existing knowledge, using virtual tools, tackling it phase by phase. That's the path.
And for you, our listener, understanding all this gives real insight, right? Into engineering projects, resourcefulness, cutting-edge automotive tech. even if you never plan to build one yourself.
Exactly. The strategies we talked about, breaking down huge problems, optimize limited resources, continuous learning, they apply everywhere, not just race cars.
So, a final thought, perhaps. What other seemingly impossible challenges could be tackled with this kind of structured, knowledge-driven, adaptable approach?
Yeah, something to ponder. The power of one determined person armed with the right strategy, learning plan, and problem-solving skills. What else could they achieve?